So good afternoon, everybody. Thanks a lot for joining us for this RADNEXT webinar. My name is Ruben Garcia. I'm the coordinator of the RADNEXT project, and I will be briefly introducing the talk and the speaker that we have the pleasure to have with us today. So hopefully you can now see the intro slide with some general information. So as most of you know, RADNEXT is a European project with the main objective of enhancing the accessibility to accelerator infrastructure for radiation effects testing. We are mainly doing this through transnational access. This is a beam that is accessible free of cost through competitive proposals in heavy ion, proton, neutron, and even more exotic beams. The next opportunity will be in March. So the month of March, we will have the proposals open. So you are welcome to submit your ideas if you have experiments that you would like to undertake in this very broad network of facilities. And of course, you are also very welcome to follow us through our website by registering and by signing up to our newsletter via LinkedIn. Of course, the topic of today is to start a series of webinars that will take us more or less around the world to discuss present and future radiation facilities. So these are really the infrastructure in which the radiation effects testing is carried out. And we have Kevin Brown with us that will give the first talk. The next webinar will be announced after today's presentation. So you will all know where this will take us for the second talk. And as I mentioned, we will record the webinar to make it available later on, but then the questions will be outside of the recording. So today we will be talking about the present and future about SE testing at NSRL. And we have Kevin Brown with us, who is a physicist that started his career in high energy physics and then transitioned to accelerator physics and has been involved in numerous projects in BNL, notably setting up the NSRL facility for radiation users that has now been running for a while and in a very successful way, and is now also leading the proposal of a new facility, the HEET facility, also in BNL, that he will be talking to us about. So I hand it over to Kevin, and thanks a lot for being available for this, and we very much look forward to what you will be telling us in the next 40 minutes, roughly.
Thank you, Ruben. Thank you for giving me the opportunity to talk to you in the RADNEXT community about what we're doing at Brookhaven. And so I'm going to talk about a few different things that we're doing at Brookhaven Lab. I want to just acknowledge the contributions from some of my colleagues. And I'm going to be going through these sort of in this order. So we'll talk about the tandem Van de Graaff, the NASA Space Radiation Laboratory, which we call NSRL, and then the new facility that we're proposing, that we're calling HEET at the moment, and then some R&D projects that we're looking at, or even further in the future. I want to, as Ruben mentioned, I want to just point out that if you're interested in what we're doing at with the HEET facility, and we are looking for letters of support. So if it interests you and you think you might want to provide a letter, you can go to this website, and we welcome all letters of support. It'll help show that the funding agencies that there's users out there who want to have this capability. This is a quick outline I described already. I'll just go on. So just a quick intro to Brookhaven Laboratory for you if you're not familiar with it. We're in New York, in the United States, here on Long Island, about halfway out in the island. New York City is over here, and lab from an airplane view looks like this. So this is the relativistic heavy ion collider where I work, which is going to run for a few more years and then will be converted to an electron ion collider. The NASA Space Radiation Laboratory is located over here, and I'll show more detail on another slide. The AGS, the alternating gradient synchrotron, is located here, and then these two buildings are where we used to house our fixed target program, and this is where we hope to build a facility for high energy effects testing. The newest machine is the National Synchrotron Light Source 2 over here. And just to give you perspective, this machine is 800 meters in circumference. The AGS is 800 meters in circumference as well. RHIC is 3.8 kilometers in circumference, so just to give you an idea of scale. Brookhaven has a long, over 70 years of doing pretty amazing research. Many awards have come to Brookhaven, but we've always been a leader in particle accelerators development technology, and goes back to the Cosmotron, which was the 3 GeV machine in the 50s, and kind of set the limits on where you could kind of go with machines of this type. And they were kind of pressed to find something to scale even larger, and they went to this alternating gradient synchrotron method, first conceived by Christophilus and then independently developed by Brookhaven physicist Courant, Livingston, Snyder, and Blewett. Most machines in the world are now built on this AGS concept. The National Synchrotron Light Source, the first one, was in 1980. So you can see the lab has a long history of accelerators. We built RHIC in the 90s and it started running in 2000. Many innovations have come out of these different machines. I won't go over them, but you can read this in your leisure. And then the latest machine is the NSRL-2, which started running in 2015. As I said, RHIC is going to run for a few more years, and then we're going to go into construction and build the electron ion collider. This just shows a cartoon of how it will kind of operate. But basically, we'll be colliding high energy electrons with ions and polarized protons, even polarized electrons on polarized protons and polarized helions. So it's quite fascinating machine. It's going to have a lot of capabilities. I'm going to mostly focus in the sort of lower energy regime, the tandem Van de Graaff, the NASA Space Radiation Laboratory, and the new proposal. Tandem's been around since the 1960s. It was the world's largest facility in 1970, and it still remains relevant. They're doing, still have a healthy program and provide very high quality beams. NASA Space Radiation Laboratory started running in 2003. And you can see here, this is in the target cave or target room. This is Trevor working on a scintillation counter detector. And then up here you have ion chambers for dosimetry, and the beam comes in over here from the right. And down here you see Adam Russick standing next to an octopole. And I'll talk more about the octopoles. They're a key to coming up with the beam shape that we developed at Brookhaven for making uniform beams. At the end of the tunnel here, it's a door. You see that'll take you into this target room. So this is the North Campus, where we have RHIC and the suite of accelerators that feed RHIC and other experiments. NSRL is over here. And you can see this is the booster, this little circle. There's an electron beam ion source. This provides all the ions. Just about any ion you can, the periodic table I'll show you later, list, and as well as the laser ion sources are located here, which have been a key technology for providing even more suites of ions to provide to NSRL and for RHIC. The tandems are over here, and they also can provide beams to RHIC and for NSRL. And LINAC provides protons and polarized protons, as well as high intensity protons for isotope production. And then the HEET facility we would run off the AGS into the old target, fixed target buildings over here. So the tandem Van de Graaff is two 15 megavolt electrostatic accelerators. This is just a layout of the facility. You can see the two large tanks here. At the moment, they support target rooms here at 11 and 13, and they can switch between them. But it's quite a nice facility. They have a long experience with radiation effects. You can see back starting in the 1980s. They still do single event upset tests, which they developed a while ago and continue to do. They do filter material irradiation chamber, which is around the mid-90s. A NASA test chamber was completed in 2019, and they're now have an award for doing heat wafer irradiation facility. And this is rather interesting. There's a paper I show a link to later that you can go to for more details. So a lot of applications at the tandem, the radiation hardness, deep ion implantation, silicon carbide for superior semiconductor devices, high temperature superconductor enhancement, and then calibrations and many other things. Just to give you a sampling of ions that they can do and what the energies are, it is low energy. But you still have pretty relevant LET and ranges for the highest energies. They also provide accurate dosimetry. So it's quite a nice facility for people interested in lower energy effects. So they do space radiation effects, micropore filter fabrication, superconductor enhancement, radiation effects for space, and then deep ion implantation. And I point you to this nice paper if you want to learn more about that. Okay, I'm going to switch to the NSRL now. This is located off of the booster. And it's a single beam line that comes out to a target room. It's attached, you can get to through this user building. If we rip away the shielding, we can see that the booster inside this tunnel over here, the beam exits from the booster. We use slow extraction, so it comes out in a hundreds of milliseconds kind of scale through this beam line, and there's a 20-degree bend here, and then the target station. The beam line is designed very specifically so that we create what we call an achromatic tune after this bend. And the achromatic tune is important in order to do the beam shaping using two octopoles, an octopole here to do the first plane, and then an octopole here to do the second. I'll try to describe that a little bit more later, but basically with these octopoles, we can shape the beam into the uniform beams that they use for radiation. And then here you see the broader view of the target room. So the NSRL was designed and built for NASA and for radiobiology work. It was NASA's we have a long relationship with NASA. It began in the 90s. They began doing their radiation effects off of the AGS, actually, in what we call the old A3 beam line. They quickly decided they needed a dedicated facility, and so NSRL was built and commissioned in 2003. I won't go through all of this, but NSRL offers many features that are very that are critical for radiobiology, but also for doing electronics testing. So the uniform beams, space relevant ions and energies, a very fast beam cutoff that's based on dose and many more features. In the more recent developments, we've over the years have developed the ability to simulate the galactic cosmic ray spectra, as well as the solar particle event spectra. This is quite an innovation that works quite well. Can switch basically energy or ions very quickly. So all of this is a good picture for radiation effects in testing in electronics, but you have to remember that the facility was built for NASA for radiobiology, which means it's not available all year long for electronics testing. And this is one of the reasons that we have been developing another proposal to do testing off of the AGS. This shows the uniform beams that we developed at Brookhaven using the octopoles. This is a paper you can go to if you want to learn more about the method. But basically, you can imagine that if you had a Gaussian distribution, and if you could fold the wings up and over to flatten that distribution, that's basically what we're doing. And so this is sort of just a conversion from Gaussian to uniform distribution. And the features, that's why you have these features here in this picture. It's very uniform in the middle regions. In fact, very highly uniform beam over a large range. And you get these spikes at the end, and that's because you don't have a perfect Gaussian, and for various other reasons, it's a natural effect. But again, you can put your samples in here and get a very uniform irradiation. Just want to try to point out that we are serving multiple masters. And so we have something we call a super cycle for managing cycles for different users. So if we're sending beam to RHIC, we would need a couple cycles or more inside of the booster that would send beam into the AGS. So this is an AGS magnet cycle. These are magnet cycles for the booster, and then this is a magnet cycle for NSRL in the booster. So you can see that we would basically be doing like a round robin between sending beam to the AGS and then sending beam to NSRL. It does mean that there's a little bit of more dead time than maybe is ideal for if you had a dedicated use, but it does mean we can be sending beam around quite flexibly to various users. And there are times when NSRL can run in a dedicated mode. And then you see here in the AGS, and in the case of HEET, we wouldn't do it this way, but instead when RHIC or EIC want beam, they would have dedicated use of the AGS, and then otherwise it would be dedicated for HEET. And I can show more about that later. So the one thing about the NASA facility that was actually designed in this way because they were only really interested in integrated dose. So good quality beam stills was really not provided. We do our best given the tools we have in hand, but we don't focus too strongly on making good quality beam stills, except when it's requested from the user. And so this is one of the things that we would improve on with the HEET facility, would be do a number of things to make a much more uniform spill temporal distribution, and I'll talk more about that later. Here's a list of ions. You can see that the energies that can be quite high, 1500 MeV for heavy ions, and up to 2500 MeV for protons. And like I said, we can switch between these quite quickly, and we can switch energies quite quickly. So it's a very versatile system. Here you can see the range versus LET that you can get to through beams at this facility. It's quite a large range over many orders of magnitude. And I think the important message maybe for electronics testing is you don't need to do delitting. You can have full systems, in their crates, and you can even have them on and running when you're doing the irradiation. They developed many tools to help support users and then provide better quality beams and more flexibility in the beams. I think one of the recent things was this tungsten collimator, which is quite an impressive device. You're getting basically 6 inches of tungsten to collimate the beams, which I think can stop up the protons up to 400 MeV-ish kind of range. So it's quite nice device. And various other devices, scintillators that you saw earlier in another picture, and energy degraders. And so if you want to do something, the key message here is to talk to us and we can probably help you. This shows an experiment set up with an electronics board with a tungsten collimator, and then they, I guess, even were using a polyethylene degrader to lower the beam energy some. I'm going to shift gears now, talk a little bit about community and national radiation needs. This sort of comes out of the US testing community. There was a council that met that's created what we call the HREC report. They looked at an analysis of alternatives for radiation effects test facilities. And there's been many kind of presentations and discussions on this for a few years now. And you can see here that out of this report, they find that there's a much higher demand than capacity in the US. This is a suppressed scale, just so you know. So, but it's still a factor of 2 difference between the demand and the capacity. And this picture doesn't really tell the whole story, because this capacity is mostly low energy. They have very little. We have very little high energy capacity, which is one reason there's a high energy recommendation to come out of the report. And you can see here, this actually fits with the HEET proposal, where by 2027 or 2028, we could be providing dedicated high energy testing with a large number of hours. This shows the picture in a different dimension. You see here there's basically 4 facilities in the US that provide heavy ion test, and these are generally lower energy facilities, except the Brookhaven, where NASA provides the higher energies. You can see that from the report that right now, about 10% of the testing is really aimed at high energy, but the demand is really looking to see high energy testing at the scale of 4,000 hours per year or more. And really, there is no facility beyond NSRL that can take you into those high energies. And this is one of the motivations for proposing a high energy facility. So I'm going to talk now about this high energy facility. So again, I'm showing this picture of the NSRL. It's located over here, Tandem Van de Graaff down here, and the HEET facility would run off of the AGS. This is where we used to run the fixed target experiments. We had 4 primary beam lines and as many as 12 fixed target experiments running at a time in these halls. They're quite large, aircraft hangar sized buildings. And I'll show a picture, a diagram later. This is the capabilities that we're looking to build into this facility. And what I'll say is that except for the energy and a focus on creating a better flux beam structure, temporal beam structure, everything you see here is provided already at NSRL, except for the high number of hours for running. But so the new facility will be designed to cover a large range of energies, even up to 2,600 MeV. This would be the equivalent of a little over 6 GeV for protons, I point this out because the AGS can actually go up to 30 GeV for protons, or up to 10 GeV per nucleon for ions. So we're not stressing the AGS by going to these energies. All the ions that can be provided are what we provide already. The large uniform beams, and the focus really is going to be on creating better temporal uniformity of the beams. Here's a layout of the facility. It looks a lot like the NSRL beamline because actually this is just mostly a copy of it. The AGS is here. It's about 1/8 of the AGS ring, and then the beamline comes out. Again, we have a bend where we have optics that creates a achromatic beam tune after the bend. Then we have a pair of octopoles where we do the same manipulation in order to create those uniform beams transversely, target room down here, and then a user facility at the end of it. The thing I'll point out is this is a building. This is the building that you saw in the diagram in the photo before, the first building. And so we'll be building a building inside that building for the user facility. You can see here the target room, it's a little bit bigger than the NSRL target room. And the user facility, this is a proposed layout. You can see here the roll-up door in the larger building that takes us into here with a loading dock. And so you could actually pull a truck up and just load directly onto the loading dock. There's a 40-ton crane inside this building. So if you have heavy stuff, it's not a problem. You can see the crane reaches, covers most of the building, just the area here. And this is a side view of the facility in the target room. And again, the target room is actually slightly higher than in NSRL. And you can see there's a smaller crane inside the target room for helping you hoist heavy equipment. And this just shows the detail of the target room. The experimenters would come in through this plug door to load their equipment in. And we have a lot of experience with these types of doors. It would be very reliable. We could be opening and closing it a dozen times a day and it wouldn't be a problem. So this just summarizes these capabilities. Again, a lot of what you get from NSRL you would get here. So I'm not repeating a lot of the things from the NSRL side of things. But you do get a slightly higher range of energies and the fast switching to simulate the galactic cosmic ray spectrum, the uniform beams, and the uniform temporal structure beams. And you could do smaller beams if you want, but certainly the optics would be capable, and it has a fast beam cutoff. So just to emphasize a little bit the energy range, here you have a simulation of the galactic cosmic ray spectrum. This is based on CREM 96 simulation. The details are down here, but basically NSRL you can cover most of this energy range, giving you about 60% of the galactic cosmic ray spectrum that can be simulated. And the peaks are down here at the lower energies of 300 to 500 MeV kind of range. And so you're certainly covering peaks of that spectrum. And at the AGS, you could cover even higher. You could go up to 75% of that spectral range. And that could be relevant if you're doing deep shielding or something where a lot of energy could be deposited in something in a spacecraft or behind some shielded area. So pretty interesting range. And this is again the uniform beams that we could provide. And I'm going to talk about spills a little bit more next. So I think I'm doing okay for time. So extraction from the AGS and from the booster is done on something we call the third integer resonance. And this type of extraction, and I'll try to explain the next slide, I think, is rather sensitive to power supply ripple. So the power supplies, aren't just coming from a battery. They're regulated supplies that have to ramp up and down, and they have a ripple on them. And that ripple is the source of that microstructure you see on beams. Now we have various ways of handling that ripple. One thing we do in the booster and we would do in the AGS is we use what we call an active filter, and I'll explain what that is in a moment. We can also play with the beam parameters inside the machine to basically accelerate or drive the particles through the resonance faster, which makes it less sensitive to this ripple in the power supplies. But the one method we would add for HEET that we don't have for NSRL is to do some feed forward or active feedback methods to high frequency quadrupoles. And I'll show a little bit about how that works also in a moment. There are other methods. In fact, we use RF empty bucket channeling for the NSRL facility, and this works quite well, but it does impose higher frequency structure on the beam, the level of 2 or so megahertz. And so that if you're sensitive to that, then that could be a problem. And so we actually want to avoid that in the HEET facility. So this just shows this third integer resin extraction. And let me explain this a little bit. So you can see it's we call it third order because you have these 3 unstable fixed points that are created by creating this sextupole resonance in the lattice of the accelerator. And basically what you have is you have just sort of a Gaussian beam. This is in what we call phase space. So this is angle of each particle versus position. In this phase space, as we squeeze the resonance down into the particles, they kind of enter sort of stable motion. They go from stable motion into this unstable motion where they pass over this fixed point and they start spiraling out of the machine. And you can sort of see that particles will step from this arm to this arm to this arm and so forth until they get to this septum. And when they get to the septum gives them a kick and they get extracted from the machine. The basic idea I wanted to get across is the reason you see this structure spill coming out of these machines is because the ripple on the power supplies is making this fixed point oscillate around. And so as it's trying to squeeze down on the beam in a stable area, it's actually modulating, and that modulation causes the flux to be modulating when it crosses over the septum and gets extracted out. And so the game is to try and reduce this modulation or follow that modulation, and so that you're less sensitive to it. I hope to explain that well enough, at least so you get the idea why we have the structure and the methods we use to try and correct it. So here's 3 different views of the structure. The first picture on the upper left is from actually CERN, and it's not the best they can do. They can do better than this, but I show it because it actually was from a workshop a few weeks ago, because it shows some of the issues that you have to go contend against with these beams. So there's a spike here, which you have to try to reduce and avoid. This can come if you try to do things too quickly, or if you there could be other effects. This might be due to high intensity in the case of the SPS. But also you can see other features. You can see here the spill actually starts quite nice, but then this structure starts to feed in. And we've seen this before in the AGS as well. And so there can be variability to this structure as things are moving along. And also some of this could be instrumental because there is a bandwidth to your monitor, and there could be other effects inside of your detector. So you have to try and roll those into into your process of trying to make a good spill for the experiment. This shows a good spill for NSRL. We've made better ones, but this one shows basically what happens with the active filter being on and with the active filter being off. You get quite a big improvement with the active filter. And this picture down here also shows the fast beam cutoff. So this is just experiments that were being done. This is but just to demonstrate how these work. So this is the active filter. It's actually fairly simple. We take another power supply that has enough power in it that we transform or couple into the mains power supply. It's being used to extract the beam, and we feed in harmonics into this active filters power supply to basically humbuck out the harmonic, the ripple in the main power supply. And you can see the effect here. This is without the active filter, and then turning it on, you see you get much better correction. This is an FFT of the voltage off the mains, and you can see we reduced this 360 hertz harmonic by a factor, by an order of magnitude, and many other harmonics got beaten down quite low. So it's quite an effective method. The other method that we would focus on is using what we call a quadrupole tune feedback. And basically you're just trying to get, you're going to be modulating the tune of the beam in the machine to just try and follow that ripple. So you're trying to get the resonance and the tune to sort of modulate together rather than not modulate together. And that's the difference you see here. This is actually from CERN. This shows actually many years ago, using an air core quadrupole, has this 20 kilohertz bandwidth. And without it, you see this bill had quite a lot of structure. This is the FFT of that, showing the harmonics are coming at very precise peaks. It's actually the line frequencies from your power grid. And then this is with the correction. You can see you can quite nicely correct these harmonics. The difficulty with this method is it is prone to drift and needs constant corrections. And so actually we see it as a good application for machine learning, but so that's one of the things we're researching. But this is one of the challenges with this kind of system. It does need a lot of babysitting to keep it going, working correctly. And then this shows a high frequency quadrupole in JPARC that they use. This is quite a nice design that we're learning more about. So for operations, what we imagine, or is not even imagine, we know that such a facility could be available most of the year. We shut down for maintenance for 8 weeks or so every summer. We actually try not to run in the summer. It's the opposite for CERN. We try not to run in the summer because its power is more expensive, and Long Island people are running their air conditioning, and so we try not to be running during that time of year. Every 2 weeks, we have an 8-hour maintenance. So beam's not available during that time, but we could be operating 24/7 over that 44 weeks. And we could have an 80% facility availability. And that, so 20% of the time we would could be due to failures. That's just our historical, we know our historical failures, so we can account that into this number. But also a good fraction of this is just providing beam to RHIC or for the EIC. And so we would have the same situation. We were sharing beam with RHIC, beams being shared with NSRL and with the isotope production. Certainly the HEET facility in NSRL could run concurrently. They could be taking different ions and different energies. So they're really not tied together in terms of how they run. They just share a little bit of time between the different programs. But certainly we could provide up to 5,000 hours, even maybe more, depending on whether we can improve on, reliability, dependability, and so forth. But on this scale, certainly more than 4,000 hours we could have available for users. Just one last slide on R&D effort. So looking further in the future, we are studying methods to create these sort of particle distributions that are useful for radiation effects. One of these methods is to use laser-driven acceleration. So this shows the basic concept, where you fire a high-power laser onto some thin metal target, and you can produce plasma that where the ions get a boost in energy from an electron cloud and from just the laser power. So you can see that you can produce high energy beams this way. And there's a lot of research going into this method, and we are could be systems further in the future would be operating based on this principle. So I'm going to stop here, summarize. So BNL has always hosted applied use experiments. We continue to support these experiments, and we'll do so in the future. The HEET proposal addresses a national need for electronics test time and could reach energies and ion mixes that are relevant for space. And we could be available for both. We'd be available for domestic and international users. We don't discriminate over here. It would not impact EIC operations. In fact, we think there are synergies with EIC in terms of cost sharing, and as well as just keeping the AGS running. And in good operation would be synergistic for the EIC. And so again, I just, if this facility and this proposal interest you, please send a letter. We welcome your feedback, and that's all I have. Thank you.
Great, thanks a lot, Kevin, for the excellent presentation, and of course, best of luck with HEET. It sounds really excellent. So we will soon stop the recording and move on to the questions. Before I want to ask you just if you can stop the sharing, I'll just put one, let's say, summary slide of the recorded part of the seminar, and then you can bring them back up for the questions, because I'm sure there will be a few. Great, thanks a lot. I will just briefly, as promised in the beginning of the seminar, so for the next edition, we will be going to Australia, at least virtually, and this is, from what I could see, one of the longest flights that one can have from New York, more or less, to Sydney. So those of you that want to take that ride, okay, I read here that we were limited, or this flight was limited to 50 passengers because it could not have enough fuel to have more. So we might be a bit tight in terms of the participants that we have here, but okay, just to announce that the next seminar will be on the 6th of April, and it will be related to the National Space Qualification Network in Australia. So this is a recent effort in Australia to build a network of facilities for also mainly electronics testing for space applications. So I welcome you to join us for that. And again, just another reminder of the opportunity of, first of all, following the information of the RADNEXT project through the various channels, and also submitting your beam time proposals for heavy ions, protons, neutrons, or other type of beams in the next opportunity window, which will be in March, so next month. So thanks everybody. We stop the recording, and I will also stop the sharing, and with this we can